Okay, welcome back. Happy Friday. So a couple of things before we jump into the new packet. First of all, we just finished test number 2. You've got it back. There's a little piece of paper that tells you the rules about corrections. You're welcome to do corrections if you want. They are due Wednesday coming up without exceptions, so make sure you do them by then if you want credit for them. The rules of the corrections are all written out very clearly. You're going to choose what kind of resource you want. There are 2 choices in front of you. Just pick one and then submit your corrections on Wednesday. I also gave everybody a blank copy of this test. You're welcome to do the corrections on the blank copy if that's easy for you, okay? All right, so that's the test corrections. The test went really well for some people and really not well for other people. It was quite a dramatic spread on this test in particular. You know how like our standard bell curve has the kind of low extremes and high in the middle. So this one was kind of like high in the A range and then high in like the C range and sort of low in the B in the middle. The high grade was 100 and 2 people got a 99 and none of those 3 people was me. I think I would have got a 98 or something on this. I made some arithmetic mistake on the coffee problem. So like I said, some people did really, really well on this, but everybody's welcome to do corrections. Okay, new packet. So again, it's got 2 components. There's the big packet and then there's a separate one piece of paper reference sheet. So everybody has the 2 new things for today? Yeah, big packet and then the separate reference sheet. Okay, and so just looking at the calendar here, we see that we're starting chapter 9 and we're going to be here for a couple weeks, and then chapter 10 for about a week, and then test number 3 will be here before we know it. When is this? May 8th, okay? In between now and then, we're going to have 2 projects. I'll hand out the next project on Monday. And then project 8 will be like a week or so after that. And then we have a quiz that doesn't exist yet, but I promise it will by the time you have to do it. It's just the kind of guy I am. Any questions on the calendar? More comparison tests. Yeah, we thought we were done with that, but I promised you we were going to come back to the comparison test. Okay, page 1. Page 1 of this big packet is also a reference sheet. We're going to skip past that to page 3. Which is where we begin today. Last thing about the packet, this is the last packet that I'm going to give you, even though there's like a week or a little more after test 3 and before the final exam. Everything up here is inside of this packet. So that's the last real handout, aside from projects and quizzes. Okay, so we'll start at the top with the daily summary. Elia. Zach. No, the other Zach. Okay, so things are going to look completely different today from stuff that we've been doing, but still under the guise of Calculus 2. So first, the definition: a sequence is just an infinite ordered list of numbers. So for example, 1, 3, 5, 7, 9 forever is a sequence of numbers. Those are the positive odd numbers, right? So you can think of the sequence as being just an infinite ordered list, or you can think of it as a function whose domain, those are the inputs, is the positive integers. So here in the bottom row are my 1, 3, 5, 7, 9 forever. And in the top row are just the positive integers. And so I can think of this function as taking the number 4, for example. Let's use S. S for sequence. Takes the number 4 and sends it to the number 7. Everybody see that? Right there. So S of 4 is 7. So it's another way to think of a sequence. Okay, so that's our standard function notation, but more common than that is to use subscript notation, where the subscript is the thing that's counting. And so we have S sub 1 is 1, S sub 2 is 3. That's saying that the second number in this sequence is 3. And you can see the second number in the sequence is 3, okay? Sequences are sometimes finite, but the ones that we're going to be playing with are infinite. Okay, so everybody understand the little counter? That subscript is just telling you where to look in the list, and then you grab the number that's in that location in the list. Okay, so let's move on to number 3. It says, let's find S of 7, and then S sub 100, and then the general term S sub n. Okay, so finding S sub 7 is not too hard by just listing the next few things, right? So what are the next couple of numbers in this sequence? 11 and then 13. So S of 7 is 13, right? So that's easy. Okay, but for 100, I definitely don't want to list all the ones getting up to 100. We got to come up with some way to think about how you get the numbers in green from the numbers in yellow, right? That's really what we're after. Yeah, so we can have different notation. Right now, I just want the number. Anybody know what the number is? Len? 199? Heard a couple of votes for 199. So is that right? Let's see. So what can you do to the number 4 that will turn it into a 7? What are we doing? If you add it to itself or double it, and then minus 1, does that work? Does it work here as well? Double the yellow and minus 1, it gives you the green. That seems like a good rule. So then we can say that S100 is really double 100 and then subtract the 1. So that 199 seems good to me. So yeah, so okay. So I think Len is seeing that the 2 and the 3 add up to the 5. Is that what you're saying? Yeah. And then jumping over here, for example, the 5 and the 6 add up to the 11. Yep. So that's another way to think about this sequence. There are a bunch of different ways to think about this sequence. So let's we can write a few different formulas here for S sub n. Okay, so let's first go with this doubling and subtracting 1. So what am I doubling? N, right? It's just the counter. So 2n minus 1 is a way to think about a formula for Sn. Or let's do S of n. This is Len's formula now. So Len is saying you add the number itself, the counter itself, and then you add the number that came right before. What's the counter called? N. And then the number that came right before is n minus 1, yeah? And we see that they're saying the same thing, right? 2n minus 1. Good. Okay, so some vocabulary. S sub 1, whatever that is called the first term. Obviously, S sub 2 is the second term. S sub n we'll call the general term. Okay, so number 5 is about to define for us the words converge and diverge. Now, before we look at the definition here, let's remind ourselves we've seen these words before. In fact, I wrote on a bunch of people's tests, only integrals can converge. Because a bunch of people wrote down x over x cubed converges, when you really meant the integral from 1 to infinity of x over x cubed dx converges, right? So I said only integrals converge. Only integrals can converge. Okay, so that was true when I wrote it, but now we're about to extend, we're about to have a new definition of converge and diverge. So it's no longer true that only integrals can converge, but in the context of this test that we just took, we were meaning the integral converges. Okay, so what does it mean for an integral to converge? It means if we look at the area forever, what kind of a number do we get out? An actual number, something finite, as opposed to infinity. Okay, same definition here, but we're just going to be looking at a list of numbers. So for example, if we look at this list of our positive odd integers and we go forever, does it converge to a single finite number? No, it's going to infinity, right? So we would say that that sequence diverges because it goes to infinity. So coming down here, our definition for 5, Kevin? Number 5. Okay, so then let's take a look at this example we just saw. We were looking at the sequence of numbers of the form 2n minus 1. And what happens to that when n goes to infinity? It's infinity, right? Just gets bigger and bigger and bigger. So again, that sequence right up above diverges. So S sub n diverges. Good? Yeah, and so it's a good point that Elia makes here. So 2n minus 1, if I think of that as being like a y equals 2x minus 1, then we can draw the line. Let's see, so intercept is down here, and it's pretty steep, so that. But then Elia says we need to erase. Why do we have to erase? It doesn't exist between, right? All we were saying is that the first number was 1, so we're out here at the point 1, 1. And the next one, what did we get when we plug 2 into that guy? 3, and the next one is 3 comma 5, right? Plugging 3 in there. So Elia's right. It's only 1, 3, and 5. It's only these single dots. And so really we should be erasing everything in between. But if the line is heading up forever, then so are the single dots, right? Yeah, you can think of the function. And who was our first reader? No, Zach talked about the continuous stuff. So our line is something continuous, right? It's got infinitely many points between every pair of points. But really, we're talking about discrete points, just the dots themselves. And that's the big difference between the continuous stuff and the new stuff here. Good point. Okay, let's try number 6. We'll go to the back. Cameron. Okay, so part A, we have S sub n is equal to n over n squared plus 4. Don't just jump directly to the limit. Let's just list the first 4 terms, getting used to the notation. S sub 1 equals, S2 equals, S3 equals, and S4 equals. You can just write your answers as fractions here. Don't worry about calculators or decimals. So S1 is really what? 1/5. Looks like magic if you don't know where it came from. Is there anybody who thinks that's magic? It's easy if you know how. Magic if you don't. Questions on this? Plugging n equals 1 into the formula. Okay, S sub 2. Yeah, it reduces. I'll write 2/8 first and then 1/4, right? And S3. 3/13 is good. 13, and then S4. Yeah, so it's 4 over 20, which reduces to 1/5. Okay, so those are the first 4 terms in our list. Yep. Okay, fair enough. So what do we think? Are these numbers approaching a single finite limit? Maybe. I mean, like maybe it's just not enough information. So how about we just jump down a little bit? Let's try S10. All right. A lot of confidence. Let's plug 10 in. What do we get? 10 over 104. So yeah, so like if you don't have enough info in the beginning, and it's totally fine, then jump out a little bit. 10th term, 50th term, millionth term, right? Eventually it should become clear what the behavior is. Okay, so these guys are heading to 0, and so we can write that maybe more formally here. Limit as n goes to infinity of the formula n over n squared plus 4. And which one of these parts of the fraction dominates? The bottom, right? Definitely way bigger than the thing on the top. So 0 is the limit. If we added all the terms together, That's what we're doing tomorrow. Monday. And using integrals is Wednesday. You guys are just predicting. You're taking away all of the mystery here. Okay, so this guy converges or diverges? Converges. So we're going to say, so S sub n equals n over n squared plus 4 converges. I wrote that. It was true when I wrote it last night. It is no longer true today because now we have another definition for the word converge. Yes. So this guy, so these sequences are going to be easy. A lot tougher are going to be when we add these guys together. And that separate reference sheet that I gave you that looks like a view into the mind of a madman, like that's complicated. And so it's going to be quite complex for us to figure out what's going on when things add up together. Yeah. Okay, let's take a look at part B. We'll get out the first 4 terms for this guy as well. S1 equals S2 equals S3 equals S4 equals. Go ahead and use a calculator on these ones. Okay, so are we approaching some single finite limit? Few people are saying no, and somebody says infinity. Now 2 is pretty far from infinity, but if you needed more evidence, what might you try? Plug in 10 or 99 or 1,000, right? Okay, so if you do like 1.2 to the 100th power, somebody have that real quick for us? 1.2 to the 100th? How much? 8 million and change? 82 million and change. Okay, that's pretty compelling that we're going to infinity, right? Okay, so then on this guy, let's see if we can figure out why this one is going to infinity. So limit is n goes to infinity of 1.2 to the n. So what's our answer in this case? Infinity, right? That one's going to infinity, which makes sense because you're repeatedly multiplying by 1.2. And what's special about 1.2 that makes it so we keep getting bigger is greater than 1, right? There's some magical thing happening at 1. Like if you kept multiplying something by 0.9, then it would get smaller, smaller, smaller. But 1 is the magical cutoff, right? So this guy gets bigger, bigger, bigger. Okay, so then our conclusion is just so S sub n equals 1.2 to the n converges or diverges? Diverges. It's okay. It's okay. I just like naming. If it has a name, we might as well use it. It's okay without though. Okay, tiny bit on the next page, and then you guys will do the activity. Number 7, Levi. Levi, 7. Okay, bounded and monotone. Monotone, have we seen this in a math class? It means always something. There's 2 choices actually. I think I heard it over here. Yeah, see, they're always increasing or always decreasing. Just has one tone, right? That's not like a parabola, which first decreases for a little while and then all of a sudden changes its mind and increases, right? But the cubic, that's something you can rely on, right? Increasing, 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 flat, looks like maybe it's gonna change its mind. No, I was increasing the whole time, right? So x cubed is monotone. It's monotone increasing, right? But x squared is not monotone anything. Okay, and then bounded, bounded just means trapped between 2 numbers. Bounded just means trapped between 2 numbers. Yeah, it's not going to infinity. That's all it says. Bounded just means it's got some cap at the top, some highest part, some lowest part. For example, 3 sine of x. What's the highest this thing ever gets? 3. And the lowest? -3. Okay, we'll change it a little bit. Now what's the highest this one gets? 1. And at the bottom, -5, right? So this guy is definitely less than or equal to -5. And definitely greater than or equal to -1. It is bounded. It is trapped between 2 finite numbers forever, right? What about our friend x squared? Not bounded, goes up forever. Old reliable x cubed, really not bounded. It goes in opposite directions. Okay, so x squared is bounded from below, but not bounded above. So if you have a list of numbers, and that list of numbers is always increasing or always decreasing, and you know that it never escapes some finite trap, then the sequence has to converge. It's got to converge to something. Same kind of thing was, it's what we saw in this first example here. N over n squared plus 4. Oh, maybe it's not. Yeah, it looks like this sequence is decreasing. 1/5 to 1/4 is increasing, but then decreasing back to 1/5. But I think at some point, probably right where we are, it's going to be decreasing the rest of the way. And it's definitely trapped between, say, 0 and 1,000,000. I mean, it's not going to escape that. So it's got to converge. In this case, it converged to 0. In number 8, let's look at this list, this sequence right here, 0.19, and then 0.1919, and then 0.191919. So is that always increasing or always decreasing? All right, so we're going to say this guy is monotone increasing. They get bigger every time. And it is definitely bounded by, and then we just got to give 2 numbers. So first of all, that will never be negative, agree? We just keep this pattern up. Okay, so it's bounded by 0 at the bottom. And would you agree that it's never going to get above 5? It's never going to get above 0.1. Well, you guys are, like really ruthlessly efficient with your bounds, whatever. Right? So it's never going to get beyond, it's never going to get out of that trap, and so it has to converge, and it is a 0.19 repeating, but really what does that mean? Because we're going forever. We're looking at this list of numbers forever. So we'll see next class really what it converges to. There's some fraction that represents 0.19 repeating forever, and we'll see it next class, okay? But this is what, I see 2 people with calculators, can't wait until tomorrow. So monotone and bounded definitely converges, although we're not exactly sure what it converges to. Yeah, what's the problem with, yeah, sine of x does not converge, right? It never, but it's not monotone because it increases and then decreases. Yeah. Okay. All right, activity I think is fairly long, so jump in and see how far you can get.